In the middle of the 19th century, chemistry was a science filled with fragments of knowledge, but lacking a clear structure. Scientists had discovered many different chemical elements, such as oxygen, iron, copper, and carbon. Each of these elements had unique properties, reacting with other substances in predictable ways. Yet there was no simple system that explained how all these elements were related to one another. To many chemists, the growing list of elements seemed almost chaotic. New substances were being discovered, but no one fully understood the deeper pattern that connected them. The man who would eventually uncover that pattern was Dmitri Ivanovich Mendeleev. Mendeleev was born in 1834 in the city of Tobolsk in Siberia, a vast and remote region of the Russian Empire. Tobolsk was surrounded by long rivers, forests, and wide stretches of land that experienced extremely cold winters and short summers. Life in this part of Russia was often harsh, yet it was also a place where resilience and determination were necessary qualities for survival. Dmitri was the youngest child in a very large family. His father had once worked as a teacher and school director, but when Dmitri was still a child, his father lost his eyesight, making it impossible for him to continue his work. This sudden change placed enormous financial strain on the family. Dmitri's mother, Maria Dmitrievna, took on the responsibility of supporting the household. She managed a small glass factory owned by the family, working tirelessly to provide for her children. From a young age, Dmitri grew up watching his mother's strength and determination. The glass factory itself became an early place of curiosity for him. The process of heating sand and minerals until they melted and formed transparent glass fascinated the young boy. It was one of his earliest exposures to the transformations that occur when substances are heated and combined. However, the factory eventually burned down, leaving the family in an even more difficult financial situation. Despite these hardships, Dmitri's mother believed strongly in the importance of education. She was convinced that her youngest son had the intelligence and curiosity necessary to succeed if he were given the chance to study. Determined to secure a better future for him, she made an extraordinary decision. Maria took Dmitri on a long journey across Russia, traveling thousands of kilometers from Siberia to the western part of the country. Their destination was St. Petersburg, the capital of the Russian Empire and the center of higher education in the region. The journey itself was long and difficult, crossing vast landscapes by carriage and riverboat. For Dmitri, the trip was not only physically demanding, but also emotionally significant, marking the beginning of a new chapter in his life. Soon after arriving in St. Petersburg, Dmitri was admitted to the main pedagogical institute, a respected institution where students were trained to become teachers and scholars. Tragically, his mother died not long after ensuring that he had been accepted into the school. Her final efforts had been devoted entirely to securing her son's future. For Dmitri, her sacrifice became a powerful source of motivation. At the institute, he began studying chemistry, physics, and mathematics. These subjects fascinated him deeply. Chemistry in particular seemed like a field full of mysteries waiting to be solved. Scientists knew that substances could combine and react according to certain rules, but the larger organization of the elements remained unclear. Mendeleev quickly developed a reputation as an energetic and curious student. He read extensively, conducted experiments, and questioned many of the existing ideas about chemical elements. His mind was naturally drawn toward patterns and relationships. Whenever he studied a group of substances, he searched for similarities in their properties, wondering whether these similarities might reveal a deeper order within the natural world. After graduating, Mendeleev continued his studies and eventually traveled across Europe to learn from leading chemists of the time. Cities such as Heidelberg in Germany were important centers of scientific research during the 19th century. Laboratories that were filled with glass flasks, chemical reagents, and instruments used to measure reactions with increasing precision. In these laboratories, Mendeleev observed how scientists studied the behavior of elements and compounds. He carefully examined how different substances reacted with one another, how their properties changed under heat, and how their atomic weights were measured. The more he studied, the more he became convinced that the growing list of chemical elements must follow some hidden pattern. By the time he returned to Russia and began teaching chemistry in St. Petersburg, the number of known elements had grown significantly. Students struggled to memorize them all because there was no clear system to organize them. Mendeleev believed that chemistry needed a simple structure that would allow scientists to see how the elements were related. As he prepared a new chemistry textbook for his students, he began carefully studying each known element, writing down its properties, atomic weight, and behavior during chemical reactions. Slowly, he started arranging the elements in different orders, searching for patterns that might reveal an underlying logic. What he was about to discover would eventually transform chemistry forever. As Dmitri Mendeleev continued teaching chemistry in St. Petersburg, he became increasingly aware of a major problem facing the scientific community. By the middle of the 19th century, chemists had already discovered more than 60 chemical elements. Each element had its own weight, behavior, and unique set of reactions. Some were metals that conducted heat and electricity, such as copper and iron. Others were gases that reacted quickly with other substances, such as oxygen and chlorine. Yet despite the growing knowledge about these elements, there was still no clear system that explained how they were related to one another. For students learning chemistry, this created a great deal of confusion. They were expected to memorize dozens of elements along with their properties, but there was no logical structure that connected them. To Mendeleev, this situation seemed deeply unsatisfying. He believed that nature rarely produced chaos without some form of hidden order. If the elements existed as part of the natural world, then there must be a pattern linking them together. During this time, several chemists across Europe had already begun searching for such patterns. Some scientists noticed that certain elements seemed to share similar properties. For example, lithium, sodium, and potassium all reacted strongly with water and formed similar compounds. Chlorine, bromine, and iodine behave in related ways as well. These similarities suggested that elements might belong to families, yet no one had yet found a system that successfully organized all known elements at once. Mendeleev began approaching the problem in a very practical way. While preparing his chemistry textbook, he wrote the name of each known element on a separate card. On each card, he included important information such as the element's atomic weight and its chemical behavior. By doing this, he could physically move the cards around on his desk, arranging them in different sequences to see whether any patterns emerged. This method allowed him to experiment with different arrangements. Sometimes he placed elements in order of increasing atomic weight, the best numerical measurement available at the time for comparing elements. At other times, he grouped elements based on similarities in their chemical reactions. As he shifted the cards into different positions, he began noticing something intriguing. Certain properties seemed to repeat at regular intervals. For instance, when elements were arranged by increasing atomic weight, similar types of elements appeared again after a certain number of positions. Metals with comparable behaviors appeared in similar places within these sequences, while reactive gases and other distinctive substances also showed repeating patterns. It was almost as if the elements were following a rhythm. This repeating pattern became the key insight that guided Mendeleev toward his greatest discovery. In 1869, after months of careful study and rearrangement, he developed a table that organized the elements in rows and columns according to their atomic weights and chemical properties. Elements that behaved similarly appeared in vertical columns, forming groups with shared characteristics. As the atomic weight increased across each row, the properties of the elements gradually changed in a predictable way. This arrangement revealed something remarkable. Not only did the table organize the known elements, it also suggested that some elements were still missing. In several places within the pattern, Mendeleev noticed gaps where no known element fit properly. Instead of forcing the pattern to match the existing list of elements, he made a bold decision. He left those spaces empty. He believed that these gaps represented elements that had not yet been discovered. Even more remarkably, he went further and predicted what those unknown elements would be like. By examining the properties of the surrounding elements in the table, Mendeleev estimated the atomic weights and chemical behaviors of the missing elements. He described how they might react with other substances, what kinds of compounds they might form, and even predicted certain physical characteristics such as density. This was an extraordinary claim. At the time, predicting the existence of unknown elements required great confidence in the pattern he had discovered. Yet Mendeleev trusted the logic of the table he had constructed. To him, the repeating structure of the elements was too clear to be accidental. His periodic table, as it would later be called, provided a simple and powerful framework for understanding chemistry. Instead of memorizing dozens of unrelated elements, scientists could now see how they fit into a larger system. The table revealed families of elements with similar properties and showed how those properties changed gradually across the rows. When Mendeleev first presented his table to the scientific community, reactions were mixed. Some chemists were intrigued by the elegance of the system, while others were skeptical. The idea that empty spaces represented elements that had not yet been discovered seemed particularly daring. But Mendeleev remained confident. He believed that future discoveries would eventually confirm the pattern he had found, and that the missing elements would one day be discovered exactly where the table predicted them to be. In the years that followed, chemists continued searching for new elements, carefully examining minerals and chemical compounds in laboratories across Europe. And gradually, one by one, discoveries began to appear that matched the predictions Mendeleev had made. After Dmitri Mendeleev introduced his periodic table in 1869, the scientific world slowly began examining the bold claims he had made. His table did something no previous system had achieved. It organized the known chemical elements into a structure that showed repeating patterns of behavior. Instead of appearing as an unrelated list, the elements now formed families with shared characteristics. Metals appeared together in certain columns. Highly reactive elements appeared in others, and gases with similar properties formed their own groups. But what made Mendeleev's table truly remarkable was not just the organization of the known elements. It was the empty spaces he had deliberately left within it. Most scientists at the time tried to build systems that fit only the elements that were already known. If a pattern seemed incomplete, they often forced it to match existing data, even if the result felt slightly imperfect. Mendeleev chose a very different approach. When the pattern suggested that an element should exist, but none had yet been discovered, he left a gap in the table rather than filling it incorrectly. Even more boldly, he predicted the properties of those missing elements. One of the most famous examples was a missing element that Mendeleev called EKA aluminum. The name came from a Sanskrit word meaning one, indicating that the element would appear one position below aluminum in the periodic table. Based on the surrounding elements and the repeating pattern of chemical behavior, Mendeleev predicted that this unknown substance would be a metal with specific properties. He estimated its atomic weight, suggested the type of compounds it would form, and even predicted its density and melting point. At the time, these predictions seemed extremely daring. Yet only a few years later, in 1875, a French chemist named Paul-Émile Leca de Boisbaudran discovered a new element while studying minerals containing zinc. The element he found had properties that closely matched the predictions Mendeleev had made for EKA aluminum. It was later named gallium. Its atomic weight, density, and chemical behavior matched Mendeleev's predictions with surprising accuracy. This discovery attracted significant attention among chemists. It was not simply the discovery of a new element that impressed scientists. New elements were occasionally found as analytical techniques improved. What made this discovery remarkable was that Mendeleev had predicted its existence years before anyone had actually observed it. Soon after, another predicted element was discovered. In 1879, the Swedish chemist Lars Fredrik Nilsson identified a new element while studying rare earth minerals. This element matched the properties Mendeleev had predicted for another missing substance in his table, which he had called EKA boron. The newly discovered element became known as scandium. Once again, the periodic table proved accurate. Only a few years later, a third predicted element appeared. In 1886, The German chemist Clemens Winkler discovered an element while analyzing a mineral called argyrodite. This new substance had properties that aligned closely with Mendeleev's predicted element, aka silicon. The element was named germanium, and its characteristics matched the predictions almost exactly. With the discovery of gallium, scandium, and germanium, confidence in the periodic table grew dramatically. These discoveries showed that Mendeleev's arrangement was not simply a convenient classification system. It was a powerful tool that revealed the underlying structure of chemical elements. Chemists across Europe began adopting the periodic table as a central framework for their work. Laboratories used it to guide the search for new elements, and teachers used it to help students understand the relationships between different substances. At the same time, scientific understanding of atoms continued to develop. During Mendeleev's lifetime, the internal structure of atoms was still unknown. Scientists had not yet discovered electrons, protons, or the atomic nucleus. The concept of atomic number, which later became the key principle behind the periodic table, would only be understood decades later. Yet even without this knowledge, Mendeleev's table worked remarkably well. In some cases, he even corrected the accepted atomic weights of certain elements when they did not fit the pattern of the table. He argued that the measurements must be slightly wrong rather than abandoning the pattern he had discovered. Later research confirmed that several of his corrections had indeed been accurate. Mendeleev's influence extended beyond the periodic table itself. As a professor and scientist, he remained deeply involved in the development of chemistry in Russia. He taught generations of students, wrote textbooks that helped organize chemical knowledge, and participated in scientific discussions across Europe. He also showed interest in practical applications of science. He studied topics such as petroleum, industrial chemistry, and the measurement of liquids. His curiosity was not limited to theoretical ideas, but extended to the ways chemistry could influence everyday life and technological progress. Despite his growing reputation, Mendeleev remained a man who valued persistence and careful reasoning. His greatest discovery had not come from a single sudden insight, but from long hours of organizing information, studying patterns, and trusting that nature followed logical principles. The periodic table gradually became one of the most important tools in science. It helped chemists understand how elements interact, guided the discovery of new substances, and provided a structure that explained the relationships between the building blocks of matter. By the late 19th century, Dmitri Mendeleev's work had transformed chemistry from a collection of isolated facts into a science built on clear patterns and organized knowledge. The simple table he had arranged on his desk had revealed one of the deepest structures in the natural world. By the late 19th century, Dmitri Mendeleev's periodic table had gradually become one of the most important organizing tools in chemistry. What had first appeared as a bold and somewhat risky proposal was now increasingly recognized as a powerful scientific framework. The successful predictions of elements such as gallium, scandium, and germanium convinced many chemists that the repeating patterns Mendeleev had discovered were not accidental. Instead, they reflected a deeper order within the natural world. As more scientists began using the periodic table in their research and teaching, its usefulness became even clearer. The table made it easier to understand how elements behaved during chemical reactions. It showed which elements shared similar characteristics and helped chemists predict how unfamiliar substances might interact with others. Instead of memorizing dozens of unrelated elements, students could now see how the elements formed groups and families within a logical structure. During this time, Mendeleev continued working as a professor and scientific advisor in Russia. His reputation had grown significantly, and he was recognized as one of the leading chemists of his generation. He remained deeply involved in both teaching and research, always encouraging careful observation and thoughtful analysis. For Mendeleev, science was not simply about collecting facts, but about discovering the patterns that connect those facts together. Beyond the periodic table, he also contributed to other areas of chemistry and science. He studied the behavior of gases and liquids, worked on improving methods of measurement, and investigated industrial processes, such as petroleum refining. Russia was beginning to develop its industrial economy, and Mendeleev believed that scientific knowledge could help guide this progress. His work on petroleum resources, for example, helped influence how oil fields were studied and developed in the Russian Empire. Despite his achievements, Mendeleev remained a practical and sometimes outspoken figure. He was known for expressing his opinions clearly and was not afraid to challenge ideas he believed were incorrect. At times, this direct personality led to disagreements with other scientists and officials. Yet even those who disagreed with him often respected his determination and intellectual honesty. In the early 20th century, scientific understanding of atoms began advancing rapidly. Physicists and chemists started uncovering the internal structure of atoms, discovering particles such as electrons and later protons and neutrons. These discoveries eventually revealed why the periodic table worked so well. The repeating patterns Mendeleev had observed were connected to the arrangement of electrons around atomic nuclei, which determines the chemical behavior of each element. Although Mendeleev himself did not live to see these developments fully explained, his table provided the essential framework that made this understanding possible. The structure he had created allowed scientists to organize new discoveries and fit them naturally into the existing pattern of elements. Dmitri Mendeleev died in 1907 at the age of 72. By that time, his periodic table had already become a central feature of chemical science. In the years that followed, additional elements were discovered and placed into the table exactly where the pattern predicted they should belong. The table continued expanding as scientists learned more about atomic structure and identified new elements both in nature and in laboratories. Today, the periodic table is one of the most recognizable scientific diagrams in the world. It appears in classrooms, laboratories, and textbooks across nearly every country. Students learning chemistry for the first time often encounter the table as a map of the elements, showing how the basic substances of the universe are related to one another. From hydrogen, the simplest element, to heavy elements created in modern laboratories, each one finds its place within the structure that Mendeleev first organized in the 19th century. The table continues guiding research in chemistry, physics, material science, and many other fields. Mendeleev's achievement reminds us that great discoveries often come from patient observation and the search for patterns within complex information. By carefully studying the properties of elements and trusting that nature followed an underlying order, he revealed one of the fundamental structures of matter itself. Through his work, the confusing collection of chemical elements was transformed into a clear and elegant system. The periodic table not only organized the knowledge of his time, but also opened the door for future discoveries, allowing generations of scientists to better understand the building blocks that form the world around us.